So can you tell us, how are the two upcoming eclipses different?
Yeah. So if we can hop to slide 4, I can explain a little bit about the geometry of what's happening during an eclipse. So what we're seeing here is just a diagram of the Earth, the Sun, and the Moon, and not to scale. And what's happening during an eclipse is in the phase of the new moon. So when the moon is between the Earth and the Sun, it just so happens to pass in front of the Sun, and it creates two kinds of shadows on the surface of the Earth. The first shadow that I'll talk about is the umbra, the inner shadow. And if you're a fan of Latin, umbra is Latin for shadow. And that's the part of the shadow where the moon is completely obscuring the sun. The penumbra, which is just outside the umbra, penumbra being partial shadow in Latin, is where the moon is casting a shadow, but it's not completely obscuring the face of the sun. So if you were in the path of the penumbra, but not the umbra, you would see a partial solar eclipse. The moon would pass in front of the sun, but what you would see was this sun turn into kind of a crescent shape during the eclipse. If we go to slide 6, I can talk about specifically what happens during an annular eclipse. So I lied a little bit when I was talking about the moon completely covering the sun. Well, a lie of omission. So the moon doesn't always perfectly cover the disk of the sun now, not just half a billion years from now when it's too far away. And that's just because the moon's orbit is not perfectly circular. It's actually a little bit squished, or elliptical as we call it. And so that means sometimes it's further away from the Earth and sometimes it's closer to the Earth. So when it happens to pass into that new moon phase and get in line with the sun and the Earth and create an eclipse, if it's in the part of its orbit, which we call the apogee, where it's furthest from the Earth, then it won't completely obscure the disk of the sun. And you'll get something called an annular eclipse. Annular eclipses are still really cool, and we have one coming up on October 14th of this year, which is, I think, 22 days from now. So I encourage everyone to view the sun during this time. And the effect that you get when you view an annular eclipse, if you're in the path of annularity, is this really beautiful, what we call ring of fire effect around the moon, where you can see the outline of the sun that's not being obscured by the moon, and it's quite beautiful.
That's amazing to see. And just a reminder for everyone, when we talk about viewing the eclipse, we want to make sure you're wearing your safety glasses and taking safety precautions. So yes, we do want you to view it, but we want to make sure you are safe doing it. Now, we've talked a little bit about both of these eclipses, but what kind of an experience is an eclipse for people?
Yeah, so if we could hop to slide 8, viewing an eclipse is really a multi-sensory experience. Usually eclipses are framed in terms of what you see, and we've been talking about what you see in eclipse today. And indeed, it's really beautiful. But there's so much more that happens, especially when you're in the path of totality. If there's a total solar eclipse happening, the moon is completely obscuring the disk of the sun. There are so many senses that you can use to experience a total solar eclipse. So in addition to seeing the corona, that faint atmosphere around the sun, the kinds of things you can expect to experience are temperature drops. So because you're essentially experiencing nighttime, you can expect temperatures like what you would experience at nighttime. So the temperature can drop by as much as 20 degrees Fahrenheit during totality, so you'll feel cold. Because of that temperature differential between where you are in darkness, in essentially nighttime, and places on the Earth outside of that path of totality, outside of that umbra shadow, because of that temperature differential, you'll get a pressure differential, and that can generate a breeze. So you'll feel a wind. Depending on where you are, animals or insects will also think it's suddenly nighttime in the middle of the day. So animals that normally get ready for bed at nighttime might start chirping for birds. Insects, grasshoppers might start chirping. On the other hand, it could become really eerily silent as creatures, wherever you're located, if you're in the path of totality, start to experience what they think is nighttime. So it's really a truly, I think, surreal experience that a lot of people have said have moved them to tears even. So yeah, a really unparalleled experience. One of the most important things, if you are planning to view the eclipse from the path of totality, is to consider what the weather will be like at any given location. I don't have the ability to forecast the weather, unfortunately. So check forecasts, check typical weather conditions at given locations in the eclipse totality path to see where you can maximize your chances of being able to view the solar eclipse. Because if there is cloud cover, obviously you won't be able to see the corona. You will be able to still experience all those cool things I talked about in terms of what you'll feel when it essentially becomes nighttime during the day, but you won't be able to see the corona. So checking the weather is important. Also, planning where you go in the path of totality is important. So the closer you are to the center of that totality path line, the longer the eclipse will last. It's not going to last any longer than 7 minutes, so it's a very ephemeral thing. But you can go from seeing it only for on the order of a minute to maximizing your time to up to 7 minutes. So thinking about where you are in the path of totality in terms of weather and how long you want to be able to view totality are both two really important things. So the moon's orbit, we already talked about how it's not perfectly circular. It's actually a little bit elliptical. The other important thing is that the moon's orbit is not in the same plane as the Earth-Sun line. It's actually slightly tilted or inclined, as we call it. That inclination is only 5 degrees, so it's very slight. But that 5 degrees is enough to make it so that most of the time we don't get a solar eclipse. You might imagine that if the moon's orbit wasn't inclined at all, if it had a 0 degree tilt to it, if it was in the plane of the Earth-Sun line, that every month we'd get a total solar eclipse with every phase of the new moon. But we don't, and that's because of that tilt. And you can think of it as like the moon passing either above or below the sun, depending on where it is in its orbit or where the tilt is in the orbit at a given point in time when it reaches the new moon. So it turns out we only get a total solar eclipse on Earth on average about every 18 months. And any given geographic location on Earth will only ever see a total solar eclipse on average every 375 years. So if you live somewhere near or in the path of totality for the solar eclipse that's coming in April of 2024, you should really take advantage of it because it's a really special event. So the Babylonians actually were able to predict solar eclipses. They figured out by observing enough solar eclipses happening and lunar eclipses, they figured out that eclipses actually repeated every 18 years-ish, 18 years and 11 days, and some more precision that I can't remember. And they did that just by observing. So they didn't have the ability to predict where an eclipse would happen, but they knew approximately what year and day, and approximately even what time an eclipse would happen somewhere on Earth. And that 18-year, 11-day-ish cycle is called the Saros cycle. So now if we fast forward to the early 1700s, an astronomer named Sir Edmund Halley actually rediscovered the Saros cycles. So he rediscovered what the Babylonians had learned 2,000 years prior, that eclipses repeat on this 18-year cycle. But he did them one better. He was able to actually predict the location of the eclipses on the Earth. And he did so accurately. He predicted there would be an eclipse through London, I believe, in 1712 maybe. And he did that using a very new theory of gravity at the time, which was Newton's theory of gravity. So he used a really precise locations of the moon in its orbit relative to the Earth and the sun, in combination with his theory of gravity, to be able to predict that an eclipse would happen in London and that it would happen at this specific time in this specific geographic area. So nowadays, we have even better theories of gravity than what Newton was dealing with back in the 1700s. So we can compute really precisely where the moon and the sun and Earth will be relative to each other out in time. And we can do it now with really high accuracy. So we can predict totality to within seconds, and we can predict eclipses hundreds of years out into the future with a precision of about minutes.